Okay, my internet apparently just went out, so apparently I'm breaking this video up into chunks now. Fortunately, the first chunk of this video, we got exactly through the end of our first example right here, so I'm going to go ahead and pick up where we left off now. So we just wrap this guy up right here. We can see that we can now finally do basic geometric things like area of a circle with integration right here, which wasn't possible until we had trigonometric substitution. And I just want to kind of say that should sort of really make sense to you in the sense that circles are like, I mean, the real definition of a circle, I mean, is mostly defined based on things like sines and cosines. It's not surprising to me that we're sort of required to bring those in to actually discuss them right here. Very close relation between trig stuff and circles right there. So let's go ahead and take a look at our next example here. So for example 2, the important thing about this, again, and I'm going to kind of scroll back up in 1 second right here, is the important thing about today is I'm not so worried about like showing you like one sine substitution and one tangent substitution, one secant substitution. I am highly confident that just as you guys are capable of using this Pythagorean identity, you are equally capable of using this Pythagorean identity. Instead, what my goal today is to show you the different types of things to expect might happen from the outcomes of your substitutions here. And so we're going to end up using this exact same substitution, in fact, for all three of our examples today, but I don't think it really matters at all that I'm not using these two substitutions. The essence of those are exactly the same. What I want to explore is why do our outputs look like they look? And for our second example here, one of the things that I want to kind of emphasize to you guys is this. You should notice, based on what we're looking at on the screen right here, that it seems to me like sine and cosine seem relatively interchangeable here. Just as I could solve sine to be 1 minus square root of 1 minus cosine squared, I could solve cosine to be the square root of 1 minus sine squared. It seems to me like even though our recommended substitution is x equals a sine theta, based on having seen the first example, it seems like it should have worked out just fine if we had done a cosine theta, right? So let's go ahead and see what happens if we instead use a different substitution other than what's recommended here, right? So, and again, all I'm saying is sine, if the whole purpose of using the substitution is to take advantage of the Pythagorean identity, in the Pythagorean identity, you could swap the role of sine and cosine and not notice any difference. So shouldn't it be the case that that should be able to be cosine and our substitutions should work out just fine? Let's go ahead and look. And so in the next example, what we're going to do is we're going to set up again the same substitution right here, except we're going to do it one way where we do x is a sine theta, and then we'll do the exact same problem, but we'll do the substitution with a cosine of theta, and we're going to kind of compare the two answers right there and see if it was equal goodness for us to use either of those substitutions and how we might compare the two solutions here. So let's go ahead and do that. So again, the thing that we're noticing right here is that the structure of the integrand right here matches that structure of that square root of a squared minus x squared. All right, so this leads me to believe that we want to make that same type of substitution as we made in the previous problem. But we're going to suggest to ourselves maybe this would have worked out if we did cosine instead. All right, so I'm seeing here, let's say, and I'm going to do my thoughts right here is that square root of a squared minus x squared. We have square root of 9 minus x squared, so it seems like we should be having a equals 3. And so we are going to do, in this case right here, an x equals 3 sine theta as our substitution. This is going to give me a dx of 3 cos theta d theta. On the other side over here, I want to say I'm gonna be the wild. There's no rules around here. It's the calculus Wild West, all right? And so I'm gonna say, you know what? Maybe it's the case that we could get away with just doing 3 cosine theta. Maybe that's all just gonna be good and fine for us right here. So I'm instead for this guy going to say maybe a cosine sub is just as good here. We're going to make x be 3 cosine theta, d theta, and therefore we're going to get a dx of negative 3 sine theta d theta, right? That negative coming out from the derivative of cosine gave us negative sine right there. So let's go ahead and see if we can work through both of these and see if either substitution is valid, and if so, are we going to get the same answer here? So, performing these substitutions, we're going to see some relatively similar stuff. And by the way, I should also say right here, and I'm going to do this one right here, it's like we want to do for our u substitution, it's like we want to do something like u equals 9 minus x squared, and then du equals like a negative 2x dx or something like that. But again, this doesn't seem like it's going to work out in these cases right here. I have x squared in a denominator. I would need like an x, a 1x up in a numerator, and we certainly don't have that. So again, our hope for the u sub here seems to fail us. So let's go ahead and see if we can work through each of these guys here. So, and I think I'm going to kind of like follow along with them like side by side so we can watch the comparisons rather than doing all of one and then doing all of another. So let's go ahead and hit it here. So in our first guy, it looks like we're going to be rewriting this integral as the square root of 9 minus x is 3 sine theta, and it's getting squared. So 3 sine theta, and that's getting squared. Down here in the denominator, it seems like I also have a 3 sine theta that's getting squared. And my dx I'm rewriting as 3 cos theta d theta. Right? On our other one, we're going to get some very similar parts here. Integral of 9 minus 3 cosine theta squared divided by 3 cos theta squared times our dx is being replaced by negative 3 sine theta d theta. Right? So I think that my move for each of these guys here should be the same, which is I want to pull this, well, actually, sorry, I'm not going to do that yet. And what I'm going to suggest to you is that my intuition tells me let's grab our constants and pull them out front of our integrand. I'm going to leave them alone here, and you're going to see some really nice cancellation stuff happen. So let's just clean up our square root terms instead. So I'm seeing here, we're going to get now square root of 9 minus 9 sine squared of theta over 9 sine squared of theta times 3 cosine theta d theta. You should notice in this case right here that there is a matching factors of 9 underneath the radical, which I can factor out as the square root of 9, which is 3. And this is a 9 sine squared of theta times 3 cosine theta d theta. Notice that one of the really nice things I'm seeing here now is I've got 3 times 3 is 9 divided by 9. So it looks like all my constants just canceled away. I'm going to pop over here and do the same thing. Keep the parentheses there so we don't get any confusion with the dot for multiplication and the negative for the sign right there. Again, I'm going to factor out this square root of 9 from the radical right there. All right. Again, it looks like 3 times 3 is 9 divided by 9. All that stuff cancels right there. All right. So I now think my next move here is it doesn't look like this negative is going to end up partnering up with anything. So I am going to pull that negative out on our cosine substitution version over here. The nice thing I'm seeing is we are getting things like 1 minus sine squared is cosine squared. The square root of cosine squared is just cosine. So it looks like my numerator now is just cosine theta over sine squared theta times cosine theta d theta. Similarly over here, the only real difference is I'm going to get the negative out front here. 1 minus cosine squared is sine squared. Square root of sine squared is just sine. So we're getting some very, very similar things, except they're actually like the exact opposites of each other right now. And it looks like I'm getting here the integral of cosine squared theta over sine squared theta d theta. And here we're getting the negative of the integral of sine squared theta over cosine squared theta. All right. So again, we're sort of suggesting that these are going to be literally the same thing as each other right here. I don't know. Are you convinced that we're going to get the same answer out? So what I'm going to do here is I'm going to do a pretty similar move on each of these guys right here, and that's because I'm remembering my derivatives that we talked about last section right here. So it seems like I'm getting cotangent squared for the left integral. It seems like I'm getting tangent squared of theta for the right integral here. And what I know is I don't know directly an antiderivative for cotangent squared or for tangent squared, but I do know that if I rewrite each of these using their appropriate Pythagorean identity, the term that's in the Pythagorean identity, I do have a direct antiderivative for. So check this guy out. I can rewrite cotangent squared as cosecant squared minus 1 using a Pythagorean identity right here. And over here, our Pythagorean identity looks like secant squared minus 1. All right here, Pythagorean identities. And the good news now is I do know an antiderivative for cosecant squared. Cosecant squared is what you get when you, or excuse me, negative cosecant squared is what you get when you take the derivative of cotangent. So this is going to be giving me negative cotangent of theta. That just is the antiderivative of cosecant squared minus, and it looks like we're just getting theta because that's minus 1 d theta right there. So we're getting a minus theta. Similarly, over here, the antiderivative of secant squared is tangent. The derivative of tangent is secant squared. So we actually know this one again, right? So there's the negative. We're getting a tangent of theta, and that's minus theta. And don't let me forget here, plus c's, right? Those matter. And so my question now is, what did we really end up with? Well, I guess what I really want to do right now is rewrite our answers in terms of x, right? So let me say something here. So what we need to do is we want to figure out a way that we can convert our theta expressions here back into x expressions, right? So what I want to do now is I want to recall what were the substitutions that we originally made. So I'm going to scroll up here and check. Our substitution for this guy was x equals 3 sine theta on the left. And our substitution over here, wait, what did I write that extra bonus stuff right there for? That wasn't right. There we go. So our substitution there was x equals 3 cosine theta there. All right. So those are the two substitutions. So if I know theta information, I should be able to get back to x by way of these two substitutions, right, for their respective integral problems that we're doing here. So we're coming back over here to remind ourselves that here we had x equals 3 sine theta. And I want to figure out what's cotangent of theta if x is 3 sine theta. So what I'm going to do is I'm going to draw the triangle. So let's draw the triangle associated with this guy. So two things. One, I want to know cotangent of theta, and for that I want a triangle. Secondly, I just straight up want theta, so it actually does seem like one of the things I want to do here is just say theta equals sine inverse of x over 3. The other thing I want to do is draw the triangle that's associated with it here. There's theta. Sine of theta is opposite over hypotenuse, so that's opposite over hypotenuse, and therefore this leg down here should be 3 squared minus x squared, right? If we add those, if we square our sides and add them together, we'll get the Pythagorean theorem will be satisfied. Similarly, over on this side over here, I'm going to make all the same statements. X equals 3 cosine theta. The two things I want to do with this guy are solve for theta so that I can convert my theta into x, and then make the triangle so I can find out what tangent of theta is going to be. So for this guy, we'll say that theta is going to be cosine inverse of x over 3, and we'll draw the triangle that will tell me Cosine is adjacent over hypotenuse, so that's x, that's 3. And this side is the square root of 3 squared minus x squared. All right? So now let's go ahead and use these to do the rewritings. Well, what are we going to get right here? It looks like my expression here is going to be negative cotangent. So I'm going to get negative cotangent. Tangent is opposite over adjacent. So cotangent is adjacent over opposite. So I'm going to get adjacent over opposite. So that's going to be the square root of the 9 minus x squared over x minus my theta term, which is sine inverse of x over 3 plus c. And it seems like this is my final answer now in terms of x. Over here, we're going to do the exact same thing. I've got negative tangent and then plus theta. So the negative of tangent, tangent is opposite over adjacent. Oh my gosh, what do you know? Opposite over adjacent. We're getting exactly matching terms right there. However, this is a plus theta, and so we are adding cosine inverse of x over 3 plus c. So it seems like we got two different answers. It seems like our answers only differ in our inverse trig expressions right here. So I'm kind of thinking to myself, let's go take a look and see how different these answers actually are, right? Kind of what I'm seeing here is I'm seeing that this term and this term match. We've got a plus c on both of them, but it seems like we have some version of unhappiness here associated with these guys right here. So what I want to do is I want to go take a look and say to myself, inverse trig functions, I'm a little rough on comparing them directly to each other. Let's go ask ourselves, are we really getting two different answers right here? So I want to compare for myself cosine inverse of x over 3 and the negative sine inverse of x over 3. Let's go do that. There's my cosine inverse of x over 3, as well as my negative sine inverse of x over 3. And what is it that you're noticing is the relationship between these two graphs right here? If I were to ask you to verbally describe to me the relationship between these two graphs, it seems like one is a vertical shift of the other. Why is that good news for us? This is good news for us because we have 2 plus c terms here that handle a vertical shift for us. So it seems to me, like back over here in the browser right here, it seems to me, and now if I go in here and I'm going to be smart. I know that I'm getting out trig stuff right here. So if we make our y step like pi, not y over 4, pi over 4, what I can see is that these are a vertical shift from one another by pi halves, right? It looks like cosine is pi, the cosine inverse term is pi halves more than the negative sine inverse term right here. Let me go ahead and snip this. I want to throw this guy into the thing right here. And let's go back over into Word here and kind of conclude what we want to conclude here. So it seems like what's happening here is I don't want to write that in red. So the point here is, if I were then to give you an initial condition at which to evaluate this integral, if I were to say, oh, and x starts at 3 pi halves, and you were to go solve for what value of c makes that true, we would find two different values of c depending on how we'd set up this problem. And one of the values of c that you would get would be pi halves larger than the other. So maybe kind of what I can say right here to kind of wrap this guy up then would be to say, let's go ahead and call this guy C1, and let's go ahead and call this guy C2. And I think that what I can say is that, let's see over here. So it should be that the cosine is larger, so we need to add more to the sine inverse one. So it seems like C1, if you add pi halves to it, you're going to get C2 right there. So the point is here, we got two different answers by doing two different substitutions, but our answers only differed from one another by a vertical shift, which is exactly handled by our constant introduced by integration there. We would just get two different values of plus, like again, if one person did this problem and a different person did this problem, one doing sine and one doing cosine, and if I gave you initial conditions, one person would find their C1 value to be pi halves different than the other person's C value, and therefore at least the graphs of their two functions would be identical to one another. So this is part of our regular lesson that we know to learn from trig stuff, which is there's lots and lots and lots and lots and lots of different ways that we can write trig expressions that are all equivalent to one another. And so just because you see two answers, that if you do a problem and you check in the back of the book or whatever, check it on Wolfram Alpha, and it's got a different solution, remember that you should still maybe stop and graph your solution and graph the solution that you've looked up and say, if our answers only differ from one another by a vertical shift and we did integration to have plus c terms, that vertical shift is just the difference between the two is handled by that constant of integration right there. So this is pretty cool. This does kind of lead me to believe that it seems like doing a cosine substitution seems to be, in a sense, just as valid as doing the sine substitution, but you need to be smart enough in your trigonometry knowledge to be able to understand why we might be getting two different looking solutions that actually, in fact, do perfectly agree with each other because they only differ by a vertical shift, and that's exactly the type of information that the plus c is always handling with the constant associated with integration right there. So that's pretty cool. I really like the way that this problem pans out to be the same, but different, but really for sure the exact same right here. So it does seem like this rule right here is slightly soft, right? When we say use x equals a sine theta, it seems like it should be pretty valid for us to do cosine theta because sine and cosine are in a sense symmetric within the Pythagorean identity. And the Pythagorean identity is what we're dependent on to bust us out of this square root term right here. Cool. Very cool. Very cool. So let's go ahead and take a look at one more problem here. We're only going to do one more today. This one's going to be a bit of a bear, but it's a very cool problem. It's going to help us find a general area of a shape that's not too difficult to describe, but is quite difficult to actually pin down the area associated with it. So let's go ahead and do this here. We want to find the general formula of this blue region, a crescent-shaped area, which is referred to as a lune. It's bounded by just the border of two circles. And the one bonus piece of information that we're going to get right here is that this isn't just, like, this is going to be a very general problem. You should notice there's no numbers, no letters associated with this whatsoever. This is just a shape in space. We're going to need to put down a coordinate system, all that kind of stuff right here, do this in general terms of R's and, come up with our own variables, all that stuff. But the one nice thing I am telling you geometrically right here is that the center of this small circle, the upper circle is the smaller of the two circles. It is perfectly in line with these 2 points of intersection right here, right? There's one point of intersection. There's another point of intersection. If you draw a line between them, the center of this circle falls exactly on that shape right there. All right, so that's kind of our one little piece of helper information. This is going to be a pretty hard problem, but that's at least going to make this easier than it could be right there. So that's our one piece of like little bonus help that we get for this guy. So our job is to find the area of the blue region. That's all we're looking to do here. So let's go ahead and say to ourselves, kind of the first thing that we need to do here is we need to identify for ourselves a coordinate system so that we can do some measurements of some things, right? So some things that I'm kind of recognizing here are, it seems like we have the center of the large circle sitting right there. And the center of the small circle, as I said, is sitting exactly in between our points of intersection right there, right? So I might draw a couple radii right here, right? Now, as we've done in the past, I think it's going to be good for us to use a little r and a big R to denote the radius of the small circle and the radius of the big circle here. So I'm going to identify a couple locations, for a couple lengths, I should say. For example, that's a radius right there, and I'm using a lowercase r because it's the smaller of the two radii. This is also one radius that's going to be right there. Another thing that I'm seeing is that this should be a large radius. So I'll go ahead and call this guy capital R, the radius of the large circle. And one convenient location, I'm going to want to be able to relate little r and big R. And one good way that I can do that is by having them go to a common point right here. So here's another radius on the large circle right there, R. And what I can kind of see based on this is that there is going to be some height between the two of them, right? There's some distance between the two centers right here. I'm going to go ahead and call that h for the distance between the centers of the circles. They are perfectly vertical of one another, right? So I've measured some lengths right here, but we still need a coordinate system so I can set up an integral, right? Because I need to say something like the integral from blank to blank, and those are typically x values for us here, right? So I'm thinking to myself that this large circle, I know I'm going to have to come up with equations of circles and stuff like that. So I'm thinking to myself, I know my general equation of a circle. For the radius of r and a center, which we typically denote as h comma k, I can write this guy as x minus h squared plus y minus k squared equals r squared, right? That's my general equation of a circle right there. Any location in space, any radius, we can use that equation right there. I'm always thinking to myself as a math person, man, I hope I just get to do math with the number 0 all day. In terms of this problem, what that means is I want to locate one of these circles to be in a very, very convenient location for me, meaning like the origin, right? So I'm going to choose this location right here to be the origin point right there. I'm going to say, let's center the large circle at the origin right there. That's going to give me a really nice, easy equation for that guy, right? I'm going to say with, or I should say, choosing the origin to be at the circle because that is a choice I am making. We can define the equations of each of these two circles, which I think I'm going to need because I'm going to have to find the area between the two of them. I'm going to need to come up with a y equation for one, a y equation for the other, and it looks like do a little bit of subtraction of areas right there. All right, so I'm thinking here that we're going to have our big circle is going to be our easy equation because we've centered it at the origin. Because it is centered at 0, 0, h and k are both 0 in its equation right here. So I'm going to be able to define this guy as x squared plus. Now, I want to differentiate between the large circle equation and the small circle equation, but they're both going to be y equals equations. And so to avoid confusion, I'm going to use the subscripts of the little r and the big R that go along with them, right? So we're talking big circle stuff. So I'm going to call this y sub capital R squared. And this should be equal to its radius squared, which is that capital R squared right there, right? So I'm just coming up with my own notation, my own coordinate system. I kind of need these things or else I can't make any measurements happen. Now for my little circle, we're going to have a little bit more going on here. The upper circle, the little circle. It seems like this location right here is still at an x value of 0, right? The center is centered at an x value of 0, so h is still 0, so I'm still going to get just straight up x squared there. But for my second term, the y value of the center of the small circle is no longer at 0. It's now at a height of h right there, which is actually kind of dumb because h is usually what we associate with x, but I don't know, I was thinking height right there, so I called it h. Whatever, the point is right here, we're going to get plus a y minus h squared, and that should be equal to r squared, our little radius. Oh, and I should be good with this guy right there, y sub r, so that I'm distinguishing between the equation of the big circle and the equation of the little circle, y sub little r, y sub big R right there. All right. So I've got my two equations of my circles. I can write those because I've built a coordinate system for myself. So I'm thinking to myself, I want to state an integral, right? Stating the integral is half the battle in all these situations. Okay, I should say, usually just constructing the integral of interest is half the battle. Today, it's going to be like 1/10 of the battle right here, as we're going to come to see, but we're going to be able to manage here. So I want to find the area of this region right here. So it seems like our area should be what? It seems like it should be the integral of. So I'm kind of thinking here, if I'm picturing like a Riemann rectangle right here, what I'm noticing is that the top of the rectangle is the height, the y value of the small circle. The bottom of our every Riemann rectangle is the height or the y value of the large circle right here. So I think I'm going to have some y sub little r minus y sub big R because this is the top versus the bottom of our Riemann rectangle, right? What are my bounds of integration here? Well, it looks like our x values are going to go r units to the left is our leftmost rectangle, and r units to the right is our rightmost. But I am also seeing here at least one nice little thing, which is that this is clearly a left-right symmetric shape. So let's at least do ourselves a little bit of a favor here and just say, you know, this is really just double the area of just the 0 to r. So what I'm really doing for myself here is I'm saying, let's go ahead and chop this guy in half up the middle right there. Let's just do the right hand half and then double it, and that'll give us the entire area of the loon. So I defined a coordinate system. Based on my coordinate system, I came up with the equations of the two curves of interest, but they're implicit right now. I need explicit equations for y. And I've come up with the integral that's going to represent the overall area. So all we have to do is just do the integration. And again, I'm going to say it right now. Basically, this entire semester so far, the challenge has been building the integral. And then doing the integration has been pretty easy. That is going to get flipped right here. This was kind of easy for me to set this up, at least, okay. And I should say, I understand if it's a little difficult for us to like build our own coordinate, like to make smart coordinate system choices and stuff like that. But it wasn't too crazy. I picked the easiest, nicest things I could think to pick. Building this integral wasn't too hard, but evaluating it's going to be a little tougher for us right here. So let's go ahead and see where we're heading with this. It looks like what I want to do now is to evaluate this, we need to solve for y sub r and y sub r. So I'm going to say need to solve for y sub little r and y sub big R. I would need to know those equations in terms of x, so I can throw them inside of my integral right here, perform the integration. So let's go ahead and take our two equations right here and solve them for their respective y terms, right? So our big one right here, x squared plus y sub r squared equals r squared. Y sub r squared is capital R squared minus x squared and y sub r squared. Now again, when we go to take our square root on both sides right here, you know, because you've taken algebra, that there should be a plus or minus. However, what I'm recognizing over here is that we are only considering the top halves of each of these circles. In fact, these intersection points represent exactly the transition between the top half and the bottom half of the small circle. For the large circle, it's very clearly only the top half that it's belonging to right here. So I'm going to be cool to drop the plus or minus and only keep the positive version because we're only discussing the top halves of these circles. So here is one of my two terms of interest there. There's y sub big R. That's my y equation for the top half of the large circle. Now for the small circle, or the little circle, it's a little more complicated here because we've got that h term involved. But not too bad. Same reasoning. I'm going to ignore the plus or minus because we're only on the top half. And it looks like what I'm getting for y sub r is little r squared minus x squared, just like we got big R squared minus x squared over here. But there's an additional plus h. And I'm thinking to myself now, what's up with plus h? Because the thing I'm noticing here is I drew this right triangle right here. I'm noticing that I do have these constants of r in the problem, but I'm noticed like that's kind of inevitable because we're defining two circles. It seems to me like we should be able to rewrite h in terms of just big R and little r, so that we only have two parameters floating around in this problem. So I think I want to kind of stop for a second and say to myself, if this is r and this is r and this is h, then I think I can write for myself the statement r squared plus h squared equals capital R squared. And therefore, we should be finding that h is the square root of r squared minus r squared, like that guy right there. Again, I'm going to go ahead and drop that positive or negative right there. In the diagram that we've drawn, h is clearly a positive y value right there, a positive vertical distance. So I'm going to keep the positive version of the square root. So this allows me then to rewrite my h term. So that I can now say that this is y sub little r equals the square root of little r squared minus x, oops, I dropped my squared on this x right there, plus the square root of r squared minus little r squared. Okay? So I've come up with my explicit equations for y for each of my terms that I need for my integral. So let's go ahead and make that guy happen here now. I'm just gonna kind of identify, just to kind of keep some organizational things here. Now let's go ahead and pick back up with that area expression. So our area, we're saying that we're interested in the integral from 0 to r of y sub little r minus y sub capital R dx. We have now come up with what y sub r and y sub capital R are going to be. And so I'm going to throw those into our integrand now. And then we'll do some strategizing. Okay, I'm going to move this down just so that we're, yeah, I want to do that, I think, just to, man, some things it moves and some things it doesn't move. And I never know what causes, hey, I'll take it. There we go. So we've got our expressions for y sub little r, y sub capital R right here. I'm subbing them in. So y sub little r is our square root of little r squared minus, I'm just copying down this into y sub little r right here. So it's plus the difference of the two r's squared, square root of them. So that's y sub little r is those two terms. I now need to subtract off y sub capital R. Y sub capital R is the square root of capital R squared minus x squared. So, I dropped an important thing right here. Remember that we're doubling this integral because of our symmetry of our geometric object right there. So this should be a 2 times and a 2 times right there. Okay, so here's kind of the thing that I'm thinking about. I want to stop for a minute and say, what the heck are we doing right here? I want to break this thing down into a couple different integrals, and here's the things I'm noticing. This is my strategy moment right here. This is a straight up constant. This is going to be easy. Right? That's the that might as well be the number 5. Right? It's just going to be the integral of 5. We're going to get 5x, and we're going to evaluate it from 0 to r. That's going to be 0 effort for us right there. These two guys look like they're going to require a trig sub, but the good news is they're going to require the exact same trig sub, right? They're of the exact same structure. We're just using a little r versus a big R. So what I'm thinking to myself is, let's just let's do this trig sub right here, the integral of square root of a squared minus x squared. When I'm done with it, I will sub back in little r to get my answer for the first integral. I'll sub in capital R to get my answer for the third integral. The integral in the middle, I think we can handle very, very easily right here. So I'm going to kind of, I don't know, restate my organizational stuff right here as this. And again, this is one of those things where if you're not organized, you just don't have a chance. So I'm going to be crazy organized here. So one, none of these integrals necessarily have to relate to one another. So I'm ripping these apart into all of their own integrals. All of them are getting doubled. That 2 is multiplying the whole dang thing right here. I think I'm going to like label these things. I'm going to call this integral A, integral B, and integral C so that we have some names right here. And again, A and C both require the exact same trig sub. So I'm going to just do one generic version of both A and C using an A instead of a lowercase r or a capital R. Then when I get my results, I will use that result to express the answer for each of the integrals A and C right there. All right. So let's go ahead and do it. So let's go ahead and just do the B integral first since it's super easy. There's like no effort really required to do the B integral here. Right? These are x values, 0 and r. This is just a constant, so all I'm going to get is 2 times square root of r squared minus r squared x, evaluated from x equals 0 to x equals little r. Well, x equals 0 makes the whole thing go to 0, so I can basically ignore that part. All I'm doing is plugging in x equals r, and it looks like I'm getting 2r square root of capital R squared minus little r squared, right? So there is one of my answers right there. I've got my B integral answer right there. I'm done with one of the 3 integrals I need to do. The remaining 2 integrals, A and C, I need to do some work for. It's a trig sub, but the work is going to be identical for both. So I'm going to do one general version and use that result by plugging back in A equals little r, A equals big R once I'm done and I get my answer. Oops, that's not what I want. I want A and C. All right. So I'm thinking of this as square root of a squared minus x squared. At the very end, as I kind of state right here, once I'm done with all my work, I'll say, and what I meant was for the capital A integral, we'll let little a be little r. And for my capital C integral, I'll let little a be capital R right there. And then we'll kind of use our general result for both of the integrals of interest to us. So the thing that I can see here is this literally is exactly the structure. I'm going to scroll all the way to the top right now. And remember, yeah, if you have exactly this, then we're going to do exactly this substitution, a sine theta. So I'm going to do exactly like, and it's literally even got the a's in there, right? So straight up, I'm doing a sine theta as my substitution right here. Right? So I've got my substitutions made here. Now, another lesson that I learned in the previous problem is I also want to convert my bounds of integration into their new variable that we're going to be using here. So I'm thinking to myself, this says to me that x over a is sine theta. And that is really telling me, so notice here, if x is 0, we'll do the easy one first. If x is 0, then this is telling me that 0 equals sine theta. And that's going to tell me that theta is going to be equal to 0 right there as well. So the bound down here of x equals 0, based on the substitution that I'm making, if you plug in x equals 0, I apply the inverse sign. Sine inverse of 0 is 0 because at 0 radians, we have 0 height. Right? For the other one right here, where we have x equals r, well, in this one, it looks like I actually have to do a little bit of work right here. This is going to give me that r over a is sine theta. And so it looks like we're going to get that theta is the sine in... Oh, man, I'm running out of room right there. Let me just move that up a little bit right here. Go up. This is going to tell me that theta equals sine inverse of r over a. And because I don't want to write that expression a whole bunch of times, I'm just going to call that b for right now. But at the end, we're going to need to kind of come back in and throw that expression back in. But I'm going to say for right now, I'm going to introduce the letter b to be the sine inverse of r over a. And that is our new upper bound. So when we had this boundary of x equals r, I solved for theta to get theta as sine inverse of r over a. That's my new bound in terms of the theta variable that we're going to use. And just to avoid writing the expression sine inverse of r over a, I'm just going to call it b, just a placeholder for right now, a lowercase b. So what are we getting over here? This is going to be 2 integral of, this is now theta equals 0 to theta equals b, as defined right there, of the square root of a squared minus a sine theta squared dx became a cos theta d theta. Let's go ahead and do the thing. Once we're done, we will be able to use little r and big R in place of lowercase a to get the expressions that we wanted for 2 of the 3 integrals that we needed for the area of the loon, right? Be organized. Right? So 2 times the integral from 0 to b. I now trust that those are the right variables right there. Right? That was x equals 0 and x equals r, theta equals 0, theta equals b. So what are we getting here now? I got a square root of a squared minus a squared sine squared. Oop, that's a, what am I superscripting my theta for right there? All right. It looks like we're going to get the same action as before. There's a common factor of a squared underneath. It's the whole reason we picked the substitution exactly like this, is just for this to happen, right? So this is going to pop out as an a. What we have left on the inside is the square root of 1 minus sine squared. Oh, come on. I hit end, dang it. Okay. All right, so here we are. So square root of 1 minus sine squared, that's just going to be cosine, because 1 minus sine squared is cosine squared. Square root of cosine squared is just cosine. So it looks like we're getting a cos theta times a cos theta d theta. Well, it looks like a times a is a squared. It's just a constant, so I'll pull it out front. Cosine times cosine is cosine squared. Oh my gosh, we're back here with cosine squared. We keep on seeing this one, keeps coming up. Cosine squared of theta is 1/2 cosine 2 theta plus 1/2. Let's go ahead and make our appropriate substitution here to continue solving. Oops, I'm opening my parentheses like I'm doing my integration. I'm one line away from the integration. This is going to be the integral from 0 to b of 1/2 cosine 2 theta plus 1/2 d theta. And I'm noticing if there's this common factor of 1/2, in fact, this is typically written as 1/2 cosine 2 theta plus 1. I should have just done it that way right there. That 1/2, this factor of 1/2 is going to cancel with our 2, leaving us just with a squared integral from 0 to b cosine 2 theta plus 1 d theta. Now we can go ahead and integrate. We've done as much as we can possibly do with our constants here, right? So a squared integral of cosine is going to give me sine, but I know if I were to take the derivative of sine of 2 theta, it would pop out of 2, which I don't have. So I'm going to introduce the 1/2 to counteract the product rule right, or the chain rule right there. The integral of 1 d theta is just theta, and we are evaluating this guy from theta equals 0 to theta equals b. All right. So now I hope that you are all good at your trigonometry here. Let's see. It looks like we're going to get a squared times. Now, I'm noticing here when you plug in theta equals 0 into this guy, sine of 0 is 0, theta being 0 is 0. So, oh my gosh, it's so nice again. Theta equals 0, zeroes out the whole thing. So all we got to do is throw in theta equals b. So it looks like we're going to be getting here 1/2 sine of 2b plus b. All right. So this is sort of good. It looks like what I want to do now is throw that b stuff in there. Then we'll have an expression that we can see is just in terms of a, and that's where we replace the a with lowercase r and capital R to use this as our result for the a and c integrals that we set up as the 2 out of the 3 integrals for our overall area expression of interest to us. So, but what I'm seeing here is I don't really want to do, so we came up with b being equal to sine inverse, what was it? We said that b was sine inverse of r over a. Notice I have to do this right here. I can't go converting into my other forms yet because sine inverse of r over a, the a term is what's going to become little r and capital R once this is my general integral that I'm trying to use for the 2 specific cases here. So I've got to do this. But what I don't want to do is get a sine of 2 sine inverse right here. So I feel like I don't want this double angle integral or double angle trig expression right here. So the other identity that I know is that sine of 2 theta we can rewrite as 2 sine theta cosine theta. Using this thing right here, I can get just individual angles inside instead of doubled angles on the inside. So it's going to be a lot easier for me to handle my function composition of a trig function with an inverse trig function here. So I'm going to do a squared times 1/2 times 2 sine b cosine b plus, this b looks like it's just going to be what it's going to be right there, right? It looks like I'm just getting sine inverse of r over a. I don't see anything else I'm going to do to play around with that b that I got right there. So what do we got? It looks like our 1/2 and our 2 are going to cancel right there. I need to be able to figure out what these are going to be now. So I've got a squared times, I've got a sine of sine inverse of r over a, that's going to be pretty easy, times the cosine of sine inverse of r over a. It looks like I'm actually going to have to put a little bit of effort in to figure that guy out right there. And on the end, plus our just trailing along sine inverse of r over a. So it looks like it's trig time here. This guy right here is going to simplify down to just being r over a, the first one, right? The sine of sine inverse of r over a. Times, what I've got to go figure out is what's the cosine of sine inverse of r over a. Well, to find this guy right here, maybe what I'll do is let's grab some stuff in blue right here and identify it over here. What I want to do is come back to my triangles. Since we're doing trig, if you're not drawing triangles, you're not figuring it out. I want to remember what my initial substitution even was here, right? I've forgotten everything because this is so long ago. X equals a sine theta, or even maybe better for me, x over a equals sine theta. So our original substitution was exactly this, just ever so slightly algebraically modified right there. And this is good because it helps me draw a triangle. This says sine is x over a. Sine is opposite over hypotenuse, so opposite over hypotenuse. And therefore, this will be a squared minus x squared down here. Right? If you square this and add it to this squared, you just get a squared. So that's my relevant triangle. And recognize here that if you were just to take the inverse sine on both sides right here, theta is sine inverse of x over a, meaning this is really just asking the question, what is cosine of theta? Right? Theta is sine inverse of r over a. Oh, wait a minute. Did I write my... Am I... Let me make sure I'm tracking my x's and my r's correctly right here. Okay, so I guess the way that I'm writing this right now is I am defining in this situation right here. It's really like I'm defining. I'm saying I'm really saying right here, let theta equal sine inverse. So I'm just going to draw my new triangle that's associated with this. We want cosine of theta from this. So this is going to tell me that we should have that sine of theta equals r over a. This allows me to draw the triangle that looks like sine is opposites over a hypotenuse. So I really have an a squared minus r squared right there. Now we wanted cosine of theta, so it seems like what we're getting from cosine of theta from this triangle. And again, this wasn't any... I got confused. This wasn't variable confusion. This is just how you do trig stuff. I would expect that we can all evaluate this expression as a standalone thing. This is obviously just one of 100 parts right here, so I'm allowing myself to get a little lost right there. But we're always getting angles out of inverse trig expressions here, so I'm just calling this a generic angle theta. We want cosine of that generic angle theta. I built the triangle that's associated with theta being sine inverse of r over a, and therefore cosine of this theta right here should be, and that's my theta right there, cosine is adjacent over hypotenuse. So it looks like I'm going to be getting here square root of a squared minus r squared over a. That's going to be my term from this guy right here, plus sine inverse of r over a. Okay, so I'm going to multiply through by a squared, and we're going to get ar plus a times square root of a squared minus little r squared. Oh, plus a squared sine inverse of r over a. Remember that this was our integral from 0 to r of, remember all the way back up here, oh, excuse me, this was 2 times our integral from 0 to r of square root a squared minus x squared. So this is my general integral right here. I now want to use that result. Sorry, I know I'm sliding up and down a lot. So now I want to use this to rewrite what I actually had for my a and my c integrals right there. So we just came up with and what I now want to do is I want to break this down to make what we called our a and our c integrals here. because we were in, so again, I'm going to scroll back up so we remember where we're at. What we wanted, what we called our a and our c integrals, were exactly what we just did, except instead of that lowercase a that we're seeing right there, we had lowercase r and we had capital R. So for the a integral, we really have that a is going to be lowercase r, and here we have that a is going to be capital R. So it should be that our integral from 0 to r of r squared minus x squared dx is going to be, and now all of my a's are going to become little r's. R squared plus r times r squared minus r squared, that's going to go to 0, plus r squared sine inverse of r over r, that's 1. It looks like here we're getting r squared plus r times 0, because that's r squared minus r squared, plus r squared times sine inverse of 1. So that should just be r squared plus 0 plus sine inverse of 1 is saying what angle gives us a height of 1, and that should be pi halves. So it looks like we have 1r squared plus pi halves r squared. So that should be, I'm thinking 2 over 2, so 2 plus pi over 2 r squared. That seems to be the result that I'm getting for a. All right, that was just common denominator right there. 2 over 2 plus pi over 2 gave us 2 plus pi over 2. That's how many r squareds we had. Similarly over here now, we had that the integral from 0 to r of square root of capital R squared minus x squared dx should then be, and I'm just subbing in capital R for a. This one's not going to collapse as nicely. In fact, I don't know if there's any simplification I'm actually doing on this guy except to acknowledge that maybe there's a capital R in all those out there. But in any event, it does now look like we can now combine all of the results that we're seeing right here into one overall final expression, right? So this should be my answer for C. I've substituted into all of the A slots capital R because we had our general integral where we did it in terms of A, but really A was representing little r for what we called the capital A integral, and it was representing capital R for what we called the capital C integral right there. So now I think I can state my final answer. Oh, and by the way, I think there's a negative in here, right? Didn't we have A plus B minus C right there? We were subtracting off that quantity here. So A was 2 plus pi over 2 r squared plus B. Remember B was our easy one that we did a while ago. There's B. 2r squared of r squared minus r squared. Minus, and that was our C integral that we just got right here. And is there any cleaning up we can do on this guy right here? Looking like not much. The only thing that I see is that we've got some two different groupings of this square root of r squared minus r squared, so maybe I'll combine those. But other than that, I think this is kind of our gross version of our general answer right here. So what I'm seeing here is we should be getting, there's a total of 2 lowercase r minus capital R copies of the square root term. Sweating after this one, I tell you what, that was hefty. But again, there's some great lessons in this one right here, which is you got to strategize. You got to decompose your parts into lots of small individual problems. We recognize that one of our integrals, the b integral, was just the integral of a constant. It was easy. We recognize that the a and c integrals weren't easy, but they were essentially the exact same as each other. So I set myself up to do one generic integral that would then be representative of the results from both of them. And then I just applied my like kind of undid the substitution that I made right there to get back to my original result right there. Then it was easy for me to just combine the three pieces that I had ended up right there to get my very gross but seeming reasonable result that we should have been getting at the end of this guy right here. Um, ooh, a bit of a bear right there to be sure. But a nice problem right here. I liked this guy a lot. It depends on our ability to set up our own coordinate system. It took me 4 whole dang pages to do this guy right here. We built a coordinate system. We were able to express our integral. We got our equations for our big and our little circles set up. So we were able to state the general integral. We strategized the whole thing. We named a bunch more things right here. And we did our work in a really, really organized fashion. And you got to remember your trig. If you don't remember your trig, you can't reconvert your bounds of integration. You can't do your substitutions to make your integration possible. More substitutions to make our to undo our substitute, more trig identities to undo our substitutions, more trig triangles to deal with our composition of trig functions right here. So this is what I was saying when I said I know that we're kind of repeating a bunch of things today, like the fact that all of our substitutions were the x equals a sine theta, but you guys can do the other substitutions. The idea, the difference between them is trivial. The broader concept of these problem solving strategies is the things that are not trivial right here. So I think it was more important for us to look at strategies rather than saying, oh, we better do a tangent substitution. I know that you guys can see your other Pythagorean identities and make those guys happen with popping some terms out of some square roots right there. So continue to be very well organized, or else you're not going to make it through with these guys here. And that is all I have for you here today as far as our trig stuff. Don't worry, we're done with our hard trig. That was all this week. And as you can see, next week we're going to move on to our hard algebra instead. And we're going to say, oh, and hey, I know that you forgot your trig. Now you relearned it. And now I'm going to say, oh, and I see that you forgot your hard algebra. And now we're going to relearn that as well. So next week we're going to pick it up with 7.4, partial fraction decomposition. Can you rip apart rational functions into being simple rational functions so that we can evaluate those guys? So for next week here, we're going to be seeing stuff that's going to be looking like how do we integrate stuff that looks like this guy right here? What do we do with that integral right there? And the answer is we want to rip that apart into two different integrals algebraically, somehow, some smart algebraic way, and then we could individually do the integral of 1 over x minus 1 easily, the integral of 1 over x plus 3 easily if they were separated. So our goal for next week in 7.4 is going to be to do the algebra to rip that up into two integrals so that we can continue on with our integration here. So that wraps us up for week 5 here. I will see you guys next week to kick it off with 7.4. Have a good one.